Hi everyone, my name is Neelesh Sathish, and today I'll be presenting my project titled Enhancing Alzheimer's Diagnosis with Vision Transformers, a deep learning approach to structural MRI analysis via global self-attention mechanisms. The main goal of this project is to improve how Alzheimer's disease can be detected from structural MRI scans using a deep learning model called a vision transformer, or VIT. Alzheimer's disease is difficult to diagnose early because the brain changes can be subtle and spread across many different regions. Traditional AI models, especially convolutional neural networks, are very strong at finding local image patterns, but they may miss relationships between distant brain regions. My project explores whether a vision transformer can do better by using self attention to analyze the brain more globally. Here is an overall roadmap of my presentation today. First, I'll explain why early Alzheimer's diagnosis matters. Then, I'll discuss why CNN based MRI models have limitations. After that, I'll introduce vision transformers and explain how self attention works. Then, I'll go through my dataset, pre-processing pipeline, model architecture, experimental setup, results, interpretability findings, and finally the next steps for this project. The main argument I really want to make is simple. Alzheimer's affects the brain in a distributed way, so our AI model should also be able to reason across the brain in a distributed way. Alzheimer's disease is one of the most urgent medical problems that we face today. In 2021 alone, about 55 million people were living with dementia worldwide. That number is projected to rise to 78 million by 2030 and 139 million by 2050. Alzheimer's is the largest contributor to dementia, making up to 60 to 70% of dementia cases. This matters because early diagnosis can give patients and families more time to plan treatment, lifestyle changes, clinical trial participation, and early care. But early Alzheimer's is not always obvious. Symptoms may be mild, and the structural changes in the brain can be hard to detect manually. This is where imaging and AI can help. Structural MRI gives us a non invasive view of the brain. The question is, can we build a model that reads these scans with enough sensitivity to detect Alzheimer's related patterns early? On a structural MRI, Alzheimer's is often associated with changes like hippocampal atrophy, medial temporal lobe atrophy, cortical thinning, widened sulci, and enlarged ventricles. The hippocampus is especially important because it's strongly connected to memory. Since memory loss is one of the most common symptoms of Alzheimer's, changes in these regions are clinically meaningful. However, Alzheimer's is not just a single region disease. It affects multiple brain areas over time. Some changes appear in the hippocampus, other changes appear in the temporal cortex, and others in broader cortical or ventricular structures. This is why the problem is challenging. A model cannot just look at one part of the image, it needs to understand how different brain regions relate to each other. Most previous deep learning models for MRI classification used convolutional neural networks, or CNNs. CNNs are very good at detecting local patterns. For example, they can identify edges, textures, and shapes in small image neighborhoods. This is useful, but it can also be limited. The issue is that Alzheimer's related atrophy can be spread across distant regions of the brain. A CNN may detect local features well, but it may also connect changes in one region and may struggle with that, with changes in another region far away. In simple terms, a CNN looks through small windows first, but Alzheimer's may require a model that can compare information across the whole image. That is the gap that my project focuses on. The research gap is that CNNs are commonly used for structural MRI classification, but they are not naturally designed to capture long range brain wide relationships. My hypothesis was that a vision transformer using a multi-head self-attention would be better model to model global context and improve Alzheimer's classification from structural MRI. To test this, I looked at two main goals. First, the vision transformer should outperform CNN baselines like ResNet 18 and EfficientNet B0 on accuracy, F1 score, and ROC-OCK. Second, the model should be interpretable. In other words, it should focus on medically meaningful regions like the hippocampus and temporal cortex instead of random areas of the scan. A vision transformer works differently from a CNN. Instead of scanning the image with convolutional filters, a VIT splits the image into patches. You can think of these patches like visual words in a sentence. Just like a language transformer learns relationships between words, a vision transformer learns relationships between image patterns. For this project, each MRI slice was resized to 128 by 128 pixels. Then the image was divided into 16 by 16 patches. This created 64 visual tokens for each slice. These tokens were passed into the transformer encoder layers where the model learned which parts of the image were most important for classification. This approach is useful because every patch can interact with every other patch. This gives the model a more global view of the brain. Self-attention is the key part of the vision transformer. Each image patch creates three pieces of information: a query, a key, and a value. The query asks, what is this patch looking for? The key represents what information does each other patch contain, and the value represents what information should be passed forward. The model compares queries and keys to decide how much attention each patch should give to every other patch. For Alzheimer's MRI classification, this is powerful because a patch near a hippocampus can attend to a patch near the temporal cortex or ventricles. So instead of treating brain regions separately, the model can learn relationships across the scan. Multi-head attention makes this even stronger because different attention heads can learn different types of relationships at the same time. For the dataset, I use a composite structural MRI dataset derived from the ADNI, OASIS 3, and IXI. ADNI provided scans related to cognitively normal individuals, mild cognitive impairment, and Alzheimer's disease. OASIS 3 added aging and cognitive decline data. IXI contributed healthy control MRI data from multiple scanners. Using a composite dataset is important because it helps make the model less dependent on one specific source. In real clinical settings, the MRI scans can vary by scanner, patient population, and acquisition protocol. The goal was to train and test a model that could handle this variation while still detecting Alzheimer's related structural patterns. The preprocessing pipeline converted MRI volumes into tokens that the vision transformer could understand. First, the input was a T1 weighted structural MRI volume. Second, axial slices were extracted from the MRI volume. Third, slices were normalized and resized to 128 by 128 pixels. Fourth, each slice was divided into 16 by 16 patches, creating 64 tokens. This preprocessing step was important because deep learning models need consistent input sizes. Normalization also helps reduce differences caused by scanner intensity or image quality. After preprocessing, each MRI slice became a sequence of visual tokens that could be processed by the vision transformer. The main model was a vision transformer with 12 transformer encoder layers. The model started with patch embedding, where each image patch was converted into numerical representation. The positional encoding was then added, so then the model still knew where each patch came from in the image. After that, the tokens passed through 12 transformer encoder layers. Each encoder layer included multi-head self-attention and multi-layer perceptron. Finally, the classification head predicted the class. For the binary task, the model predicted cognitively normal or Alzheimer's disease. For the multi-class task, it predicted cognitively normal, mild cognitive impairment, or Alzheimer's disease. This architecture was designed to capture both local visual patterns and long-range relationships across the brain. I tested the model on two classification tasks. The first task was binary classification, cognitively normal versus Alzheimer's disease. The second task was multi-class classification, cognitively normal versus mild cognitive impairment versus Alzheimer's disease. This task is harder because mild cognitive impairment can be an intermediate stage and may share features with both normal aging and Alzheimer's. To evaluate the model, I used accuracy, F1 score, and ROC-OC. Accuracy measures the overall correctness. F1 score is helpful when class balance matters because it combines precision and recall. ROC-OC measures how well the model separates classes across different decision thresholds. I also benchmarked the Vision Transformer against ResNet 18 and EfficientNet B0, two strong CNN-based baselines. For the binary classification task, the Vision Transformer achieved strong performance. It reached 98.6% accuracy, a 97.9% F1 score, and a ROC-OC of 0.992. The ROC-OC is especially important because it shows that the model was not just memorizing one cutoff point. It was able to strongly separate cognitively normal cases from Alzheimer's cases across thresholds. This result supports the idea that global self-attention can capture meaningful structural differences in MRI scans. However, binary classification is the easier task because Alzheimer's and cognitively normal scans are usually more different from each other than mild cognitive impairment scans are. That is why the multi-class was important. In the multi-class task, the vision transformer still performed strongly. The model achieved 95.4% accuracy for cognitively normal versus mild cognitive impairment versus Alzheimer's disease. This is important because mild cognitive impairment is more difficult to classify. It can represent an earlier transitional stage, so the brain changes may be more subtle. The vision transformer outperformed the CNN baselines. ResNet 18 achieved 87.8% accuracy. EfficientNet B0 achieved 89.1% accuracy, and the VIT achieved 95.4%. To suggest that the VIT was better at handling complex classification where differences between groups are more obvious. The main reason is likely the model's ability to connect distant but related brain regions through self attention. The vision transformer performed well because global self attention allows it to capture long range dependencies across the brain. Instead of only focusing on small local features, the model can compare information across the hippocampus, cortex, ventricles, and other regions involved in Alzheimer's related structural change. For interpretability, I use GradCam and attention rollup. These methods showed that the model focused on medically relevant regions and especially the hippocampus and temporal cortexes. This is important because high accuracy alone is not enough for medical AI. A model also needs to be explainable. If it focuses on regions that match known Alzheimer's biomarkers, then the results become more trustworthy. There are definitely still limitations. The model needs more external validation across scanners, sites, and patient populations. Future work should test it in more clinical settings and compare performance across different MRI protocols. Overall, this project shows that vision transformers can provide a more sensitive and interpretable approach for Alzheimer's MRI classification than traditional CNN based models can ever do. Thank you for watching my presentation, and I hope you have a great day.